Richard, someone wants to know why you keep looking up.
Well, I could say that I'm always an optimist, but I've got monitors above my camera here, and I've got two of them higher than my webcam here. And on one of those monitors, I have a live view of the sun, which I'm going to share with you. And I'm just checking out to make sure it's still in focus and the telescope is tracking properly. So forgive me if I look up every now and then or look down at my notes. I'm just trying to give you the best information that I can.
Okay, and with that, we're going to go ahead and get started. Welcome, everyone. Thank you for joining us. My name is Sandy Breimer, and I'm one of the librarians here at the Mission Viejo Library. And this is going to be an exciting presentation, some live solar viewing. I know I've personally never done anything like this, so I'm really looking forward to it, as I hope you guys are. I just want to mention a couple things before I turn it over to Richard. This program is part of a grant that the library received, and along with that grant, we've made some STEM activity kits that patrons can check out. There is a kit called the Sun and Moon STEM Activity Kit that's available for checkout to patrons. It includes sunoculars, binoculars, some different STEM activities, some STEM craft activities, some different books, all kinds of materials. So those are available for checkout now. And then I just wanted to, we have a lot going on at the library, but I'm just going to promote, we've got summer reading. It's back, it's live. It's going to be fabulous, starting June 15th. So keep an eye on our webpage for that. And we will also, Richard will take questions. Go ahead and put them in the Q&A session, and he'll answer those at the end. And with that, I'm going to turn it over to Richard.
Thank you very much, Sandy. And I'm excited to be back here sharing with you some information about our sun and live views of our sun today. I've got a few slides to share with you just to set the stage for what you're going to see and how we're actually going to manage this magic today of looking at the sun safely and in real time. And what we're going to see. I want to lay the groundwork for what we're going to see, as well. So I look forward to your questions. I look forward to sharing with you. The sun is performing beautifully today. It's really an exciting object to look at if you have the right equipment, and we do. So let me share first a little time-lapse video of the sun. This was taken a long time ago. By a NASA spacecraft. And I'm going to play this video here. The sun rotates just like our Earth rotates on its axis. The sun also rotates. It takes about 27 days to rotate on its axis. And here's just a few hours compressed down into a few seconds here of rotation of the sun using very specialized telescopes aboard spacecraft that are in orbit around the sun or orbit around the Earth, pointing at the sun. We can see there's a lot of activity on the sun. Now, obviously, you can't see this with your naked eye. In fact, you don't want to look at the sun at all. It can hurt your eye. And you certainly don't want to look at the sun with a pair of binoculars or a regular telescope or a magnifying glass, anything like that will damage your eyes very, very quickly. So quickly, you wouldn't be able to stop it. So any kids out there, please don't try to look at the sun with your eyes or a regular telescope or a pair of binoculars. You need very specialized equipment to look safely at the sun. So do this safely. And that's one of the things Science Heads loves to do. We're a nonprofit here in Orange County, and we love to set up our solar telescopes and let people look at the sun safely. It's so easy to find in the day sky, and it's so interesting if you have the right equipment to look at it. Just looking at this video here, you can see a lot of stuff going on here, and we're gonna share a live image in just a minute and see a lot of the same kind of thing. But first, let's talk about that equipment that we're using. Here on the left hand side of this slide is a picture of the type of telescope that we're using. It's called a hydrogen alpha telescope. It's designed for one purpose, and that is for looking at the sun, our star. It doesn't work on anything else. You can't look at the moon. You cannot look at Jupiter. You cannot use it to look at any of the planets or their moons or anything else in the sky. At night, it's totally useless. But during the day, it shows amazing images of our sun. And it does this using very specialized filters. First off, the filter in the front there blocks about 99% of the light that's getting to your eye. Or if you have an imager or a camera attached, it's blocking almost all of the light that's coming from the sun. The sun is extremely bright. And if we try to look at it, we would hurt our eyes because of how bright it is. It may be 93 million miles away, but it's producing a heck of a lot of light. And it's very, very bright. And we feel the heat that it produces, and we see the light. It also produces radiation and other wavelengths like ultraviolet wavelengths. So our skin gets tanned and burnt if we're out in the sun too long. That's all from the energy that the sun is producing. So we block with this telescope, we block most of that, about 99% of it. And then we separate the rest of the light, that 1% that goes through it, into a very special wavelength of red light called the alpha, hydrogen alpha band. And with this telescope, we're looking at the sun in this very narrow band of red light. And that's what's going to give us some amazing images. Now, there's other wavelengths of light that you can look at the sun with. You can look at it in various ultraviolet wavelengths. You can look at it in X-rays. You can look at it in near infrared. And we're looking at it in the visible wavelengths, but a very small band. If you think of a rainbow, a rainbow has a number of colors. One of those colors is in red. If you split that into the various types of red and keep on splitting it and splitting and splitting it, you get down to this one wavelength that we're interested in and we're using today with this telescope. So that's how this telescope works. Now, what can we see in this wavelength? Well, you can see sunspots. Sunspots, of course, are dark dots or spots on what we call the surface of the sun. The sun, of course, doesn't have a surface, nothing solid that you could walk on if you could stand the heat. But what we call the photosphere, where light leaves the sun, goes out into space, and some of it in our direction, that's what we refer to as the surface of the sun. And sunspots are dark spots on the sun. They're dark because they're a few degrees cooler than the area surrounding the sunspot. So in our earlier session, we talked about the temperature, the surface temperature, the average surface temperature of the sun, about 55,000 degrees. 5,500 degrees Kelvin. A sunspot is a little bit cooler than that, and it may be 1,000 degrees cooler than that. And because of that, it looks darker than the surrounding area. We call it a sunspot. It's still very hot. You and I couldn't survive if we went there. We'd be way too hot. We'd get burnt up like a crisp in no time. But it is a cooler area. And we believe it gets cooler because of a concentration of the magnetic fields that are emanating from the sun. The sun is a very, very powerful magnet, or millions of magnets, if you want to think of it that way. And sometimes the magnetic fields coming out of the surface of the sun concentrate in an area, and we believe that's what forms a sunspot. So we're going to see some sunspots today. There's one big sunspot region that we'll talk about. We're also going to see what's called a plage. And a plage is it's kind of the opposite of a sunspot in many ways. It's a concentration of heat, and it looks hotter, it looks whiter. And we're going to see a plage on the surface of the sun today. And then if you look at the top right corner of this slide, you'll see a prominence shooting out from the edge of the sun. We're going to see a whole bunch of prominences, and you often do. Prominences are solar material shooting out into space. Now, the sun is a ball of gas, and most of that gas, particularly in the photosphere, is highly ionized. It's got a negative charge or a positive charge. And because it's charged, when this material comes close to one of those magnetic fields which are coming out from the photosphere, that plasma or that material will shoot out into space following that magnetic field. And it's really interesting watching these prominences over time, because you'll see them forming and shooting out and arcing and coming back to the surface of the sun. And then often you'll see them go backwards and come back to where they originated. It's kind of fun to watch. The other amazing thing about these prominences is that each of these prominences that I'm going to be sharing with you live, they're 2 or 3 or more times the size of the whole Earth. They are huge. You could fit 2 or 3 Earths in many of these prominences. They're so big. Remember, the sun is 93 million miles away on average. It may look small in the sky, but it's huge if you were to get up close to it. So these prominences are huge as well. And often these prominences are not just shooting out from the edge of the sun, but there's many of them shooting out directly towards us on Earth. And we see them as what we call filaments. That's down at the bottom left image there. You see an arrow pointing to an example filament. It looks like a dark line. That's simply a prominence shooting straight out. And we're going to see some of those in our live image of the sun today as well. So let's take a look at a live image. I'm going to drag over my my software. I've got a camera or an imager connected to my hydrogen alpha telescope, trained on the sun. And first thing you'll notice is a whole bunch of prominences shooting out from the edge of the sun. Let's zoom in on one of those. So I'm going to zoom in here and go up here. And we can zoom in a little bit more. Let's take a look at this prominence, the top right edge there. And we can see it. It's probably a loop. We're not seeing the center of that loop. Some of it is visible to us. Some of it is a bit hidden. But again, that's 2 or 3 times the size of the Earth. We look over on the left side, we can see another prominence there shooting out, and not all of it is visible. And below it is a little tiny prominence. So I'm talking about this prominence here, and there's a tiny prominence over here. And again, this is solar material, plasma, highly ionized gas, mostly hydrogen, that is shooting out into space, following the lines of the magnetic fields that are emanating from the sun. The sun is a very powerful magnet. So let me go back over here. Let's take a look at another prominence here. I think this one may be my favorite today. Check out this prominence shooting straight out into space. That must be a huge magnetic field. And sometimes those magnetic fields, I mentioned that they often loop around and go back to the photosphere. Well, sometimes those magnetic fields break. They can actually break, and that's probably what's happened here. So this may have been a loop earlier in the day, or maybe yesterday, and now that material is kind of lofting around, floating around in space. When a magnetic loop like that breaks, it can send a whole bunch of plasma and a whole bunch of highly energetic particles out into space. And that's what we call a corona mass ejection, or CME. This may have been the other part of the magnetic field right here. I'm not certain, but it may have been that loop was a huge loop like that. And a lot of that material that we don't see now anymore may have been shot out into space. Sometimes it shoots directly in our direction. And I'll talk a bit about that a little bit later, how that can affect us here on Earth, because it can have huge effects and something that we need to pay attention to. So over here, we see a smaller prominence. And if we go over to the other edge of the sun, we see a small prominence over here as well, kind of light. It may look small, but believe me, that's a couple of times the size of the Earth. So it's actually a huge object or thing that's emanating from the sun. And let's go back up here. And there's where we started, this huge, massive prominence over here. So we see the prominences very easily along the edge of the sun. I'm going to share with you another video of a prominence forming. This is from a website called spaceweather.com. Again, that's spaceweather, one word, .com. And we see a video here. This was over the period of about an hour, looking at a specific area, region on the sun. This is was very, very recent. Last night or this morning. And it's what we call a solar flare. Now, I mentioned a coronal mass ejection. That could also often be associated with a solar flare. But a solar flare doesn't necessarily have to eject particles or material. What it's actually ejecting is high energies, radiation like X-rays. And that's what you see there. The really bright spot there, it's producing a lot of X-rays being sent out into space. And I want you to notice something else. There's kind of a wave of material that's happening while that solar flare is occurring there. Watch this area right here. Look for a kind of a wave that goes from left to right. We call that a solar tsunami. Turns out that the sun, the photosphere and corona of the sun can produce quakes and tsunamis. Now, this is not water. It's not like a tsunami here on Earth, which happens, often or sometimes after an earthquake, if it occurs out in the ocean, a huge wave of water can wash up over, tens or hundreds of miles. But that solar flare that we see in this video is producing this tsunami of plasma sweeping across the solar surface there. Now, to see something like this, you have to take images over a period of time. It doesn't happen just, in a second. It happens over a period of an hour or more. And that's what this astronomer did, was to document this over an hour. And notice what it says here. That tsunami is traveling across the sun's surface at 560,000 miles per hour. Very fast. So you get the idea that the sun is an incredibly dynamic place, very powerful place, huge magnetic fields, huge tsunamis and quakes. So it's not just sunspots, it's not just prominences. There's a lot going on the sun. Pretty exciting stuff. Let's take a look at some more live video of the sun. We go over to the other side here. We can see some prominences that are shooting out directly at us. Here's one. Here's another. They look like dark lines. So these are prominences shooting directly in our direction. So it's one of these guys, but on the side of the sun facing us. That's what we call a prominence. And if we scroll down a little bit here, we can see what we call a plage. See that white area there? It's a hotter area. Remember, a sunspot is a cooler area. A plage is a somewhat hotter area on the surface or photosphere of the sun. Now, let's go up here. And clear that. We can just barely make out a sunspot here. The telescope isn't quite tuned to show that. And I think we see another sunspot grouping over here. Sunspots are cooler areas, as I mentioned, and astronomers have discovered that there is an 11-year cycle of increasing and decreasing sunspots. And if we go back to our slides, I can explain that. So we've noticed over the decades that we've been studying the sun, or couple of hundred years that we've been studying the sun now, that there are cycles. If we plot the number of sunspots that we can count on the photosphere or surface of the sun, by time, we see that there's these cycles increasing and then decreasing and then increasing and decreasing. We're currently exiting cycle 24 and entering cycle 25. And we've seen over these cycles a decreasing in what we call the maxima, or the maximum number of sunspots that we've counted on the sun. these last few years, the sun has been pretty quiet, has not produced a lot of sunspots. So we suspect in the next few years, that's going to reverse. More sunspots will be formed. Why is this happening? We really don't have a good explanation yet. Astronomers are studying this and coming up with theories, testing those theories. So kids out there, if you're in school now and you're really interested in astronomy, stay in school, get a college degree, a master's or a PhD, and you may be able to discover why our sun goes through these kinds of cycles. And we believe other stars go through cycles like this as well. What's also interesting is that, you remember I mentioned that prominences shoot out from the surface following magnetic fields. And I also mentioned that sunspots are associated with denser magnetic fields emanating from the sun. The cycles we've discovered also reverse polarity. So cycle 24, the one edge of the sunspot may have been a positive and the opposite edge of the sunspot may have been a negative. The next cycle is the reverse. Positive may be on the right, on the left, and negative may be on the right now. And we can actually get a mixture of sunspots from the two different cycles during the minimum. And we can measure the polarity of the sunspots to determine what cycle they belong in. So we're currently we're seeing a sunspot currently. Sunspot, it's called AR2822. And there's potential of a strong solar flare associated with it. And trying to figure out what cycle it's currently in. But the spaceweather.com website gives you all of this type of information and can show you recent image of the sun, so you can see what sunspots are there. So again, here's that website, spaceweather.com. There's that sunspot that this picture was taken earlier in the day, AR2822 is the designation of that particular sunspot with that X-ray flare and solar tsunami that I shared with you. Pretty interesting stuff. Let's go back to our live view, see what's happening here. Over a period of time, you can see things change. So that prominence hasn't changed much, but now we're getting a better look below it at what may be a sunspot grouping forming there. Notice it's kind of motley, the right limb of the sun here. You can see kind of dark areas and light areas. The sun, the entire photosphere of the sun is very, very active. There's what we call cells of plasma rising and falling, probably billions of them. I don't know how many could possibly be there, but the sun is huge. You can fit 10, 11 Earths across the face of the sun. So it is huge in of itself. But these cells are plasma, mostly hydrogen, ionized hydrogen, rising, cooling, falling again, heating again, then rising again, cooling, falling again. So this convection of heat and energy coming from the depths of the sun up to the surface or the photosphere of the sun. And that's what causes this mottling, this dark areas and light areas. This telescope isn't powerful enough to show you individual cells, but that very first image I shared with you was taken with a NASA spacecraft. Those telescopes aboard those NASA spacecraft show some wonderful detail of those cells. Let's take a look at this prominence that's shooting straight out. And boy, we're seeing a lot more shooting out now from it. Looks like there's maybe another prominence right next to it, or a component of it. Here's another prominence, and yet another one over here. And this sure looks like maybe a sunspot grouping down here, or an area that may form into a sunspot. We'll see what's going on here. And there's that plage that we were looking at, I believe, a little bit earlier. Now, why is the sun so important to study? Let's think about that, consider that for a few moments, and then we'll come back here, get some final views, live views of the sun. So I talked about sun cycles, the sunspot cycle. You know, the sun produces a lot more than just sunlight. It produces heat, of course. We can feel the heat on our bodies from the sun. It takes about 8 minutes for light to reach us from the sun. That's based upon the speed of light and the distance the sun is from the Earth. I mentioned that solar flare. I showed you the video from the spaceweather.com website. It's producing X-rays. And X-rays travel at the speed of light. So when a flare occurs, 8 minutes later, we'll see those X-rays if they're coming our direction. The sun also produces a lot of radio waves, as we see here. That often can be heard on a regular radio, just static in the background. More importantly, and of concern, and a reason why it's important to study our sun, is the energetic particles and the solar wind and magnetic storms that the sun can shoot out into space. Now, energetic particles, these could be protons and heavier, atomic nuclei shooting out into space. And this can affect astronauts who are in orbit around the Earth, or more importantly, astronauts who are traveling to the moon. They have practically no protection from these kinds of particles spewing out into space. The astronauts in orbit around the Earth are protected by the magnetic field of the Earth. The magnetic field shunts those particles away from the Earth, protecting the astronauts who are living aboard the International Space Station and are traveling to it or back from it. But when astronauts were traveling to the moon, the only thing that was protecting them was a very, very thin layer of aluminum, and that was not sufficient to protect them for these high energy particles coming from the sun. So we had to be very, very aware of what the sun is doing when we had those missions, the Apollo missions. And NASA is planning on sending astronauts back to the moon in 2024. We hope to have astronauts in orbit around the moon. And again, they'll have to be protected from those energetic particles. What can these particles do? Well, they can damage the DNA, possibly causing cancer. they can cause visual effects. Even the astronauts aboard the International Space Station occasionally report flashes of light that they see. And those are energetic gamma rays coming from outer space primarily, but that can be of concern. And then flares can create what I referred to earlier as a coronal mass ejection. Magnetic storms can occur. These high energy particles and plasmas sometimes get pointed right at the Earth, and that can have severe effects on communications, our electrical grid, and our health as well. So take a look at the next slide here as an example of effects here on Earth. Energetic particles or electrons coming from the sun can damage spacecraft in orbit around the Earth. So too can flares, the protons, high energy particles, damage satellites and interfere with communications with our GPS satellites, for example. Can affect the avionics or the electronics aboard aircraft that we fly in. And these magnetic storms from the sun can also induce current in our power grids. Now, back in 1989, the city of Quebec, Canada, and parts of upstate New York and the Northeast lost power for hours because of a magnetic storm and high energy particles and plasma spewing from the sun directly towards the Earth. Entire electrical grids shut down or were shut down to protect the equipment. And it took days to repair some of the damage that was done during that period of time. Back in, I think it was 1859, there was a similar event that was even stronger. It's called the Carrington event. And back then, we didn't have a lot of electronics, and we didn't use electricity for a lot of things other than lamps. But the excuse me, the Carrington event affected communications. Back then, we used telegraph. We had wires run across the country, and you've probably seen it using little keys. Trained people would send Morse code messages, and these high energy particles and magnetic storm produced current on those lines that stretched for hundreds of miles. And those operators actually got shocks from that event. I don't know if anybody was seriously injured, but it disrupted communications back then in 1859. So what's happening on the sun in real time can have a real effect here on Earth. There's even some studies being done to determine if there's any relationship between these type of events, these X-ray flares and high energy particles, and heart problems that people may have. But we know for sure that these kinds of events can degrade electronics, can damage satellites, and can shut down entire energy grids. So watching the sun, keeping an eye on what it does, and warning people when there's a big event is an important part of what NASA and scientists at NASA employs, what they do. There's some really cool things that these events can cause. You probably have all heard of the Northern Lights or the Aurora Borealis. There's a version of that for the Southern Hemisphere, the Southern Lights or Aurora Australis. These happen at high northern latitudes, upstate New York, Canada, Alaska, sometimes Washington State, Oregon. Beautiful displays of high energy particles reaching the Earth's upper atmosphere, charging the nitrogen and other gases at that altitude, and producing very colorful, beautiful displays. If you've never seen the Northern Lights, I definitely recommend taking a trip sometime to the northern latitude states, staying a bit. Every now and then they occur. I mentioned how the magnetic field of the Earth protects the astronauts in space. When high energy particles impact those magnetic fields, they get shunted around the Earth, but some of them go down the poles, southern and northern poles, and create the northern and southern lights by energizing the nitrogen and oxygen in the atmosphere, producing some beautiful colors sometimes and these beautiful ribbons to see. Let's take our last look at the live sun here. So let's see what's happening to those beautiful prominences that we were looking at in the plage. Boy, that prominence is lasting for quite a while, isn't it? And that the partner that it has there is around. And this plage here is becoming more prominent. You know, again, the sun is rotating on its axis. So in the few minutes that we've been watching, it's moved a little bit. We're seeing some of the cell activity in the southern limb here. Let's go up north and see what's happening there. There's that chevron type of prominence that's shooting out into space. That's an interesting one. And that massive prominence up there is still there with the maybe that sunspot grouping. Pretty interesting stuff. So I see we have some questions here. How do you measure the temperature of the sun? Obviously not with a thermometer. That's absolutely right. I can't go to the sun and measure it with a thermometer. But color is a good indicator of temperature of the surface of the sun. So scientists use what are called spectrometers to measure the temperature of the sun. And at different levels, different layers, there's different temperatures. The surface is about 5,500 degrees Kelvin. It gets hotter inside the core, of course. And one of the great mysteries right now that we don't really understand is the coronosphere, the outer layers of the sun that you don't see with this telescope presently, the layer where the prominences are shooting out into, that can get up to 1,000,000 degrees Kelvin or hotter. And we don't understand why. So it's something that astronomers are studying, trying to determine why would the coronosphere be hotter than the photosphere and the chromosphere. It's a mystery that we haven't solved yet. There's another question here. Is there an estimated amount of plages on the sun? Well, that's a really good question. I'm probably not qualified to talk about plages. To my knowledge, there is no similar kind of cycle for plages as there are for sunspots. So the plages come and go, and there's a lot to be learned about what forms them and why they form. So I'll try to find an answer for that and post it on our website, scienceheads.org. I want to point out here, we see some clouds here on Earth passing in front of the sun, but that contrast is helping with these filaments. Look at the dark filaments that we see there. Again, those are prominences shooting straight out at us. So sometimes clouds can help a little bit when looking at the sun, and it's getting quite cloudy right now. The sun must be passing behind a cloud here on Earth, but it is helping with those prominences. Very interesting. So thank you for those questions. Let's spend a few more moments here looking at the sun in real time. Oh yeah, certainly went behind a cloud that time. So it's probably going to be a while yet before it emerges from that cloud here on Earth. I want to thank you for joining me today and letting me share some of the exciting stuff about the sun that I'm familiar with. If you want to learn more about what we call heliophysics, there's a great science website that NASA hosts at science.nasa.gov/heliophysics. And if you want to learn about the spacecraft that NASA has in orbit about the Earth or around the sun, there's links there for the SDO, the Solar Dynamics Observatory, and the SOHO spacecraft, and the Stereo spacecraft, which has been decommissioned. There's also, I should have added to this, a link for the newest spacecraft, the Parker Solar Probe. For the very first time, NASA has sent a spacecraft to actually sample the chromosphere, the material in the outermost portion of the sun. That's called the Parker Solar Probe. The Parker Solar Probe is getting as close as 3.8 million miles to the surface of the sun, and it's able to handle temperatures up to 2,500 degrees Fahrenheit. That's hotter than lava, by the way. So imagine that, a spacecraft made out of titanium and metal, being able to withstand such high temperatures. And it's got a heat shield that allows it to observe the sun and actually capture some of the particles that are flowing from the sun, some of the solar wind, as we call it. That Parker Solar Probe is traveling at upwards of 690,000 miles per hour. Amazing spacecraft. So do a search on Parker Solar Probe to learn more about that spacecraft. It's been there just a few months now. It's got a 7-year mission, I believe. It's going to get closer and closer to the sun over time. It's using Venus for gravity assist to get closer. It's in this kind of elliptical orbit, this exaggerated ellipse around the sun, allowing it to get close to the sun on every subsequent pass. Really interesting spacecraft. So hopefully that will continue to collect some amazing information about the sun. Again, as Sandy mentioned, this presentation has been brought to you via a grant from the Institute of Museum and Library Sciences. I want to thank the museum for hosting us today. I invite you to learn more at our website and the NASA websites. Sandy, that was a lot of fun, wasn't it?
That was fabulous, Richard. So it's been a great morning. I appreciate all your time and knowledge that you have shared with us. So that was really amazing. There is a survey that I would please ask participants to answer for me. It's part of our grant. Lauren has just put that in the chat. You may get a separate email from me as well with that link, just so I can ask you. It's 60 seconds tops, really not painful at all. So your feedback is always appreciated. And that's it for this afternoon. Again, Richard, thank you so much. This has been a lot of fun. So appreciate it.
You're very welcome. Thank you. And hope everybody keep on looking up, but be careful when you look at the sun. Don't use a telescope. Do it safely.
Yeah.
Bye-bye now.
Bye.